A very good evening to one and all. Center of Excellence in Safety Engineering and Analytics, CoE-SEA, welcomes all its dear participants to week 39 of the weekend talk on Safety Engineering Management and Analytics, SEMA. The event is conducted under Azadi Ka Amrit Mahotsav, which commemorates 75 years of India's independence. We begin this event with this beautiful slogan, Asatoma Sadgamaya, Tamasoma Jyotirgamaya, Mrityoma Amritamgamaya, praying to the Almighty to help us, to lead us from ignorance to truth, from darkness to light, and from death to immortality. Now let me welcome our dignitaries onto the virtual dais. We have Professor J. Maiti, who is the chairman of CoE-SEA, Professor O.B. Krishna, who is the convener of the event, and our expert speaker for the day, Dr. Saptarshi Mandal. He is a user research specialist in human factors, Center of Excellence at Microsoft USA. He pursued his UG degree in the Department of Industrial and Systems Engineering, IIT Kharagpur, and obtained his PhD with the focus on human factors from the Department of Industrial and Systems Engineering, University of Oklahoma, USA, in the year 2020. He has worked as a management consultant at PwC India and is currently working with Microsoft. His current work aims to develop statistical analysis and machine learning tools to improve the usability of products in the wearable and AR VR domains. His research focuses on the application of statistical tools to analyze and improve complex human integrated systems. For example, air traffic control operations, industrial safety, etc. He specializes in the application of and machine learning techniques to evaluate human cognitive abilities. He is a recipient of numerous awards, which includes the Best PhD Dissertation Award, PhD Dissertation Excellence Award, Graduation License Scholarship, Best Master's Thesis, and Best Student Paper Award at HSES Annual Meeting in 2016. We are very privileged to have you here today, sir, and we are very happy to hear you. Now, let me welcome Professor Maiti to formally welcome our expert speaker. Over to you, sir.
Yes, thank you, Suin. Thank you, Dr. Saptarshi Mandal, for accepting our request to give your expert speech on improving safety using data analytics and eye tracking. Regarding Dr. Mandal, he is our alumnus. BTech from our department in Industrial and Systems Engineering, and then industry experience. After that, the PhD from Oklahoma State University. The interesting part of Dr. Mandal, what Suin couldn't tell because she doesn't know this. Basically, that you all know that IIT students primarily think of that, okay, do something in analytics or some kind of IT related things and have a very good job with a lot of money, and these are all good things. But Saptarshi is a little different kind of person. Actually, he first looked at the utility of his work, his research, his contribution to the society, and that attracted me the most when he came after his PwC, that tenure. He said, I want to do something which will be useful to the society so that I can contribute there. And he started working in this area, particularly human factors. You know that it's a very important area nowadays. It is becoming more and more important. And he demonstrated that, yes, this is one area where one can be very much successful. And he also implemented in his research many things. I can say from the engineering ergonomics, the user's interface design, analytics, machine learning, and also human sensing technologies. So it's wonderful. I can tell that such a young, at this age, he he actually demonstrated his huge caliber. And I really appreciate Dr. Mandal, your that focus in this particular domain and doing so good in this particular area. And CoE-SEA, IIT Kharagpur, really uh, happy to note it, acknowledge it, and I am sure that you will be, as usual, you are helping us in many ways, and you will continue in doing this. And today, the audience will be immensely benefited from your lecture. And for the audience, I can tell you these are the new ways of looking into safety and the allied domain, the interface between safety or from the interface design point of view where users are more important. With this, I welcome Dr. Mandal for this presentation, for his expert presentation. And Dr. Mandal, now the stage is yours. Thank you so much.
Professor Mighty, the best part I liked was the still young one. that adjective I still like the best. So with that going on, are you guys able to see my screen? Because I'm new to Webex, so I have to ask these things. Okay.
Yes, sir, we can see.
Okay, so directly diving into the content. So today's presentation is about how we can improve safety using data analytics and eye tracking. And particularly, I applied this confluence of analytics, eye tracking, safety in the aviation domain. So this will be a particular few case studies of safety related to aviation domain. So let's just directly dive in. So before understanding how all these come, we need to understand few things: how air traffic control works, what are its various components, and then what are the basic components of eye tracking and how they come together on the same platform to improve safety. So first, what are the components of an air traffic control? So it's similar to traffic police lights we have seen while driving the road. However, on the sky, you don't have signals, so you need some other measure to maintain the traffic there. So this is a chart. You see there are 5 parts. One is the tower. When the plane is on the ground, it takes off. You need somebody to instruct them, like take off now or take a taxiway on the runway or the ground. Then when they depart, after they reach certain altitude, there is a part called TRACON. I'll go into details, what are the aspects. Then you have an en route in the middle. Then when the plane is arriving to some destination airport, then you have again a TRACON thing. And finally, when it is about to land, you can come under the control of the tower. So as you see the picture depicts, so there are 5 different air traffic controllers responsible for this whole journey from start to end. So the first component comes as the departure and the arrival. So these are the controllers which you can normally see in the airport. You have big towers, right? In the airport, you have a very big tower, and people are sitting there giving instruction to the pilots when they have to take off, when they have to line up and all. So basically, they control the ground clearance, the departure and the arrival within the 5-mile radius of the airport. And they employ both, they use their naked eyes also to look around the region, and also binoculars, and there are also computer systems where. Then next comes the TRACON, which is also called controlling terminal airspace. It is between the radius from 5 to 40 miles of the airport. They control the incoming or outgoing aircraft or the traffic within that region. And also till the aircraft reaches a 10,000 feet altitude. You have most of the time heard when you take off, your seat belts are not switched on till you reach at 10,000 feet. So that's why this 10,000 feet has a importance, because it changes the controllers. And lastly, the high altitude, which is called en route, you don't generally see these people because they use satellite connection and sit mostly underground or in a very different facility outside of the aircraft. So these are for high altitude. So these are the 5 aspects of air traffic control, or 5 parts of air traffic control. However, we might think the workspace or the visual feel or what they look at might be similar. It is not the same. So currently we will focus only about the control tower and the en route, because Traken is almost similar to control tower with more advanced communication system. So we'll address these two aspects. The airport control tower, you have seen such big towers in the airport, and how their workspace looks like is like this. It's both same for the arrival and departure. So this is the visual feel for the air traffic control. You have computers where they look at the layout, which is not visible from the naked eyes. Then you have the ground runway area or the taxi area where you line up, slowly move to the runway, and then take a runoff on the runway. And the en route is completely different from this, where you have a controller looking at a very big screen with many numbers and a radar. And it's a very dark room in reality. I've visited few of here in the US facilities. So it's like literally very tense environment, because one blip is a high speed jet. And if you just are not attentive for a few seconds, it might lead to something very disastrous, like a head-on collision. Because there is a famous Hollywood movie, I think Arnold Schwarzenegger was there. He was playing a father role, and some mishap happened due to air traffic controller not paying attention. So now you can understand it has real life safety consequences, because you want to be safe. Another important aspect of this, why air traffic controller is important. Normally, these aircraft trajectories are predetermined, optimizing with fuel and for time and other aspects. However, one thing which we cannot control yet, and which changes very dynamically, especially if you go up in atmosphere, is the weather phenomena. So it is so dynamic, even with the most accurate prediction models or the satellites, you still need a manual inputs, like an expert actually guiding. Like suppose a thunderstorm develops over some mountain areas, it happens very rapidly, and you have to avoid that thunderstorm. So it's very difficult for a pilot, even though they have sensors, but it's still very difficult to navigate their way, because practically in the daytime, if you're a pilot, you will just see a white screen if it is cloudy and having thunderstorm, and night it will just a dark screen. So you need somebody manually controlling and giving instruction, because there are other aircraft flying in the same vicinity. And from safety point of view, what's the standard operating procedure that I believe followed throughout the world is a 5-mile radius horizontally and 1,000 feet vertically difference upward and below, to maintain a safe, you can call a safety spare or ellipse around aircraft, to call it a safe way. So if any other aircraft comes within that range, then it's it is considered loss of separation. So you have to always maintain this loss of separation as per standard operating procedure. So now, once we have a brief idea what the air traffic controller does, why it is an important thing, it's actually a big safety concern if they don't get to do their job correctly, or we don't have enough controllers. Now let's see how eye tracking all of a sudden comes into. So what aspect of eye tracking can we use to address the safety concern? So what is the current problem is the air traffic volume is rising at a rapid pace. Like it is expected to be doubled. This is with respect to the FAA study, Federal Aviation Administration in US. I'm not sure about the traffic volume around the world, but I'm expecting a similar range. Even we can see how Indian air traffic is increasing at a rapid pace, because the cost has come down and people are preferring to take flights, because it is almost similar to like what you can, a Rajdhani Express train and an Indigo flight to a nearby city, almost similar range. So people prefer taking the air route. However, the current air traffic control training process involved, it ranges from almost 3 to 6 years. However, one aspect is highly the success rate is very variable. Like statistics that we have here in US is only 50% of the people pass that rigorous test, because you have many issues like color blindness. Then you have other cognitive abilities that need to be satisfied if you have to be part of that job. So we don't have enough controllers as per the forecast by the FAA to handle this anticipated increase. Now, people can say, okay, hire more people and get more people as air traffic. However, there is one problem with that. Training is not that easy. It is time consuming and costly. And we need to improve the success rate. Like the current success rate is 50%. So you are thinking, okay, let's get in more people. We can train them in 3 to 5 years. We'll get 100 air traffic controller. However, at the end of the training period, you find only 30 could pass the minimum barrier. So what's the next question? How we can improve this success rate? So that's why this question arises when I was doing my PhD research, and this research came from the FA. They funded my research study with my professor, and they wanted to know how we can improve this training process. So the question now, one possible solution, here comes eye tracking. What my professor previously found in his research, that he did a pilot study where he was working with expert pilots, and he was recording their eye movement data on the screen in a very simulated study. And he found that after recording those eye tracking videos, he showed those videos to normal students in the university and found out that the training, when those novice students were exposed to the same videos of air traffic control, their false alarm rate actually reduced. What is the false alarm rate is? In reality, the air traffic is happening in 3 dimensions. However, when you see that on a radar screen, actually is projected on a 2D. So many a times, novice people will have a illusion that 2 aircraft might be colliding on screen. However, they might be actually flying far away from each other in reality. So as a result, the air traffic controllers think that there is going to be a possible collision in future. So what they give some traffic management instructions like, okay, go up to, suppose there are 2 aircraft A and B, they give instruction to aircraft A, you should go climb down your altitude to B, okay, you turn right. However, every such instruction from air traffic controller is expensive because they have to change their route, which impacts their fuel usage and time. And there are many other aspects because it's not just 2 aircraft colliding aircraft in the airspace. If you maneuver one, it affects the trajectory of all the nearby and all the pre-scheduled aircrafts. So it's not so due to that one maneuver, you have new emergent safety problems. So that's why every instruction matters, and there is a time constraint attached to it. Like, when do you notice that conflict? Some aircrafts have very high speed, some aircrafts are flying at very low speed, some aircrafts are going through some wind phenomena or weather. So many other parameters which are beyond your control are there. It's like in the scenario. So if you give an instruction, you have to take into account all those various aspects. So as a result, it's always good if you can manage a traffic by giving less instruction because of all those parameters. And contrary to our belief, which I also think was true, but it is not true in reality, is even the air traffic controller gives an instruction, it's not necessary the pilot is going to follow unless it's like mayday instruction. So if it's actually negotiation happens, you won't believe. It's like what we negotiate in market, like if you're trying to buy a fish, being a Bengali, I'll give a fish example. Like suppose you are buying a katla fish. What will happen? They will charge a high price and you will negotiate, no, I can't pay this, I will have to pay. A similar negotiation happens in air traffic control and with the pilot. Suppose the air traffic controller gives you need to climb up 1,000 feet. The pilot will say, no, I can only do 500. I don't want to. You won't believe it's not that I have to, but I don't want to, because some low budget airlines, I'm not sure whether you have noticed this. If you're flying a low budget airline, you have more turbulence compared to a high budget airline. It's not completely true always, but sometimes I have experienced that because I realized why one possible reason is, suppose you have a weather phenomena and air traffic controller says you have to avoid that weather buildup, like suppose there is a thunderstorm happening. So here in US, if you fly Spirit or Frontier, they are budget airlines. So if the threshold is you have to avoid that by maybe suppose 10 miles, Spirit will say, no, 5 miles, I will manage it. It's fine. have a southwest, and if you go up higher, they will maintain a 10 because they want a good customer experience for their passengers. So depending on which airlines you are flying, you might experience different frequency of turbulence or different amount of turbulence. So this is one of the reason which can be avoided, but they don't avoid it because of the other issues of optimal theory, like optimal fuel usage and other. So yeah, going ahead from that, so coming back to the problem, how eye tracking can be useful, it's like my previous research shows that if you expose experts scanning strategy or eye movement data to novices, their false alarm rate reduces. So that's actually efficient. You are getting better your job. Starting from this point, I developed what we can go do going ahead. So now, what is eye tracking? Many of the participants or the audience people might be familiar. I'm just giving a brief. This is from the TOBI website. So what it does is, if you're suppose you have a tracker, eye tracker on your camera, step one, what it does is it consists of a camera with has some infrared light. It emits infrared lights, and it illuminates to your eyes. So that infrared light falls on your pupil. Then it takes the image of your pupil. First, it locates, it creates a 3D image of your head, positions your eyes with respect to that model, and then it calculates where your gaze is falling. Using some inherent algorithm, they calculate the XY position and how long you are looking. So these are the basic two aspects that these eye tracking, most of the commercial eye tracker that gives. Just a second. And move this. Yes. So what we generally obtain from an eye tracker is position of your eye fixation, like where you are looking for some time. So that XY coordinate, if it is a 2D display. For 3D eye tracker, it will be XYZ. It will be in the wild open. And how long you are looking for 1 second, 2 seconds, 3 seconds, like that. You have other parameters or other aspects that you can also capture. It's like blinks. When you are blinking, that camera is missing. The infrared cannot capture your position. So you can obtain that data. When did you blink? How many times you blink? For how long you blink? Because that has implications on other aspects of eye tracking research. If you are doing how effective is a visual, like the interface and all that, these parameters are very useful. Then you have pupil dilation, which is very highly correlated with workload, stress, how difficult, or fatigue, mental fatigue. It's becoming a very new research, because even talking about the aviation, pilot fatigue is a big phenomenon, because many human errors or pilot errors are a result of pilot fatigue. So FAA, NASA, and all those are looking into what schedule or what aspect impacts pilot fatigue. One of my colleagues, Salim Nairi, he did a great research on this, like how long duration flights affect pilot fatigue, how sleep schedule affects pilot fatigue. Then you have the same pilot flying an aircraft which has multiple destinations, how that affects their fatigue, like the effect of the day, age, and all those aspects. Another eye tracking component that you can find out is the smooth pursuit. It is different. In real life, you do it. It's like, suppose you are reading and slowly moving your eyes. So that's called smooth pursuit. You are not fixating at a certain location, but you are slowly moving your eyes. So that's called smooth pursuit. And there is another aspect which I think I missed here. It's called saccade. It's like quick movement. So in reality, you don't just locate here. Your eyes are actually moving a zigzag fashion or a random in a Brownian motion kind of thing. Then you move to another location. Then you fixate there for a certain duration, and such and so and so forth. So this quick movement between two consecutive eye fixation is also known as saccades. Yeah. So what are the two components of interest to most of the research we have is eye fixation. There are two aspects of it: continuously fixating at a region. The duration generally varies from 60 to 100 milliseconds. That's when you define that it's a fixation. And there is also duration involved, like how long you're looking at that particular location. Another aspect is the saccade. It's a rapid eye movement that I just called. Now, once these two aspects are defined, how do we generally visualize it? Now you have a sequence on the right, which is also called scan path, like the trajectory or the path of how you scan. So you have A, B, C, E, F, G. So these are the circles which are eye fixation. The center of the circle is the actual XY location of the fixation. And the size of the circle is proportional to how long you fixated on that location. So it is proportional to the duration. So you have these fixation, and the directed lines are the saccades between successive fixation. There is another way to represent eye tracking data, that is scan path sequence. What you do is you translate that figure or a trajectory into a string of characters, where the first location you can name it A, B, and C, so forth. Why it is useful is sometimes when you have a screen with many like objects on it, you can see why it is relevant after we go into much detail in the presentation. So suppose you have numerous targets. Now, and it's a big display. Now, if you start using the actual location, which is called the pixel position of your eye, you can't really extract meaningful information, because not every part of the screen is useful for our research question or the question we unravel. We want only pinpointed, like, are they focusing on this particular region or that particular region? So these regions are sometimes in eye tracking literature is also called area of interest, some called region of interest. So you want to only understand whether the fixation occurred within that area of interest or not. If it has occurred, you name that area A, and all the fixation that fall upon A are considered same with respect to mapping. So then you translate that eye tracking data into a sequence of characters. It becomes much more easier to analyze instead of using the pixel location. So depending on the context or the research question you want to answer, you can choose a variety of methods. Either use the actual pixel location, or you can use a scan path sequence by mapping them with the AOIs. So now, once we have some understanding what the air traffic controller does, what's the safety concern there, how eye tracking can help in there, what are the basic components of eye tracking. Now I'll directly delve deep into what one of the two researches that I did in PhD. So you can say, okay, let's just collect eye tracking data of an expert and just utilize it. But however, the reality is far more challenging than that. It is not straightforward to directly analyze expert air traffic controller data. And why it is? Because first, even if you have to use the data, you need to map those eye tracking to some objects. And here, the targets or the aircraft representation on the radar screen of the computer, they are dynamic in nature. They are always moving. And in en route case, which we talked earlier, when they are flying over 10,000 feet, these are not actual aircraft. You see some abstract representation of theirs on the radar screen. And these shapes, abstract shapes of the aircraft, they can change their position, obviously, because they are actually flying. Apart from that, they can change their shape because the air traffic controller can move those representations, because sometimes they have to zoom in a sector, zoom out. There are various aspects of that representation, which I'm not covering here. So what you think is a target which changes shape and position with time. That's why the first challenge is we have to map our eye position with those objects. As a result, once this is one challenging, how do we map with dynamic targets? Then you have complex eye movements, because in some cases, suppose you are filling up a form, you scroll down the website and put submit at the end. So you start from the top left corner, you fill up information, and then from left to right, and you slowly go vertically down to fill up the form one by one, and then you press up. So there is a certain predefined order where how you need to do the job, like do A first, then B, C, and then at the last submit button, which is at the lower right corner. However, in terms of air traffic control, there is no such predefined strategy or predefined way or how you should scan the radar. As a result, it's not a homogeneous data that, yes, this is the pattern they are going to follow. So it's not that very right. There's as many air traffic controller, as many possible strategies. So you're dealing with basically in data analytics term, unstructured data. So you don't know what is the standard way of doing it. You take what the expert do as standard and then build upon that. On top of that, you have huge amounts of eye tracking data is huge. Even for a few seconds, you will have huge amounts of data because it's a video data. You have to map it with the eye movement data. So now an air traffic controller generally works for 8 hours a day. Imagine the amount of data in gigabytes or terabytes you are generating. Although we may not be analyzing a terabyte data, but gigabytes for sure come if the data is combined with the video and the eye tracking. And the last challenge is heterogeneous strategies. Experts do their own way, even though most of them, all of them go through the same similar training process, but how you scan, there is no predefined strategy or standard operating procedure. Many people scan like a linear fashion. You start from the left of the screen, you do a zigzag, but linear drift. Then you have circular motion. Then you have inward spiral, outward spiral. You start from the center, you slowly move out. Many people do a quadrant basis. They mentally divide the screen into 4 quadrants. They do quadrant 1. They can have individual strategies for different quadrants. And sometimes it is not only like a bottom-up approach that the controller decides their own strategy independent of the traffic scenario, but the content or what they are looking also drives some. So it's a combination of the traffic movements, their patterns, the controller's own strategy, and some random aspects. So today's talk will address few research, mostly 2 big research questions with respect to which are essential for utilizing air traffic controller data, air traffic controller eye tracking data. The first is how can we visualize? First, even if you have to use, you first need to we always do a plot, basic scatter plot or a bar plot of the data, and then we go for advanced analysis. In this case also, first objective, how do we visualize the visual scanning strategy for a dynamic case? So for this, what I developed during my master's work was, can we use the network or what we call graphs, which has nodes and edges, use that framework to model eye tracking data? You will see the benefit of it in subsequent. So here we are using dynamic networks. So it's basically a network, static network with a time component attached to it. And how can we use that to facilitate our visualization, like how the scanning strategy is changing, which targets are getting important over time, or basically the evolution of the scanning strategy. The second, how do you represent this change? So there comes, like you have a network, but it has some limitation. How can we use other visualization strategies to extract meaningful information from that network? You will see the utility in coming slides. And the third question is, sometimes it is not always, so when you have to use the eye tracking for directly teaching novices, you have to expose them to the actual scan paths of the experts. So the raw scan paths are very complex. You cannot make out any meaningful information most of the time. How you can simplify that representation and then use it for training? For that purposes, I developed a clustering framework, which has other components, which helps you, a decision maker, to decide few important parameters, which I will discuss later, like how they get a quantitative framework to choose the optimal parameters and simplify this scan path representation. So let's dive into the first question. Which time I have? I have 30 minutes, right? Just asking. Okay.
Yes, sir.
So the first, okay, thanks. Let me know when you 5 minutes are left. Okay, I'm not looking at the time here. So the first question is, so the first question here is, how do we visualize this visual scanning strategy for dynamic environments? So 4 steps. First step is, how do you map with the dynamic? So first step is, you have these objects which are changing their shape. So you have to create region of interest, or AOI, for these individual targets. So that you see there is a rectangle box and a small header coming out of it. That's a typical representation of an aircraft for an en route case, when they are flying above 10,000 feet. So you create an area of interest, which is dynamic in nature because it is changing the shape. The area of interest also changes its shape with the change in shape of the aircraft. So here it's a convex hull of the points, and it is slightly bigger than the aircraft. The reason is, even though all the commercial eye trackers say they are pinpoint accuracy, however, in reality, even they sometimes mention that the inaccuracy is 1 degree. What it translates to is, if you are sitting 100 centimeter from this display, there might be offset of 1 centimeter on the screen. So if you're looking at X, Y, the eye tracker might note X plus 1 centimeter or Y plus 1 centimeter. So this is the offset. However, this offset is not constant. It gets impacted how far you are sitting, then how big your screen is, whether the controller has eye issues, like if they're wearing glasses, the offset increases much more because of the reflection from the glasses. So it's the offset is differential in nature. As you move away from the center of the screen, your offset changes, and it's not linear. It actually increases. The farther away, I'm not sure whether it's a square or exponential relationship, but I have observed while doing the experiment the maximum offset of a 4 centimeter, which is huge, like this big on the screen. So in real life, you might look at aircraft A, but the tracker will say you are looking at B. So your conclusion can be completely wrong if you don't take these into offset. Why these are important for dynamic cases? Because here objects are moving, they can overlap on each other. So when you have to first map, you have to take into account all these. So you see this is a data of 20 minutes data. You see there is nothing useful. You cannot make out anything. So you have targets which are shown in green, and you have red points, which are the fixation, and the red lines as sakar. So how to utilize such a complex thing? What you do is, now you see the utility of the scan path sequence, like condensing all those complex visualization in a sequence. You name those aircrafts. Here AYA is a aircraft A, which I code name. And another interesting thing is, in the sequence of character, you see a bracket A comma C. That's an overlap. That's how you can represent that fixation happened when A and C were overlapping, and the fixation happened on a common region. So you have no way to infer whether they're looking at A or C. So you just take both in them into account. So this actually gets very complex. You have longer overlap sequence for very dense traffic regions when they are actually approaching the airport. So there is an inherent challenge with scan path sequence, but it's like an inevitable challenge. Now you can use this sequence to change into a tabular format. How you do it? It's like you take into account how many times you moved. So here you have a row A, B, C, D, and all the targets. Then you have a column A, B, C, D. The table actually notes down the transition you made from the frequency of transition happened from aircraft A to B. So you condense that fixation information into a transition information. How many times you transition from one aircraft to another. And you have a nice tabular thing. Once you are transforming that very complex eye tracking data into a tabular format, you can represent that table into a graph. This graph has other components. The color you see, that's proportional to the total time you have spent on aircraft A. Then you have the directed edges, which shows the amount of transition. The thickness of the edge shows the transition amount. It is proportional to the amount. And the direction shows the transition happened in which direction. So you have nice such properties, changing from that complex to this static network. It is much easier to visualize. And you can see you made this tabular format has been reduced into the graph. So you made 2 transitions from A to B. You fixated more duration on A. However, A and D are similar in size, but the color of A is more red. Here, red means more duration, yellow means less duration, and you have a map from yellow to red. So D means, although you visited D similar number of times as A, however, the time you spent on D is much less compared to A. So you can infer that A was very significant if we have to analyze this graph. That means, and now you have to translate this information to radar. That means aircraft A was very crucial. Now you can look into their altitude and all aspects, why they are crucial. So these information you can easily teach to the novices that you should focus more on A and make significant amount of transition from A to B. Might be that A and B were on a possible collision track. So these information which are useful for the traffic control, you can teach. Next comes, however, in reality, what you have, this is the actual representation of what an en route controller look at. See, the blue one is the weather phenomena, and you have such aircrafts which can change their shape. You have some information of what are the aircrafts, their altitude, in which direction they're moving. However, you note these position of aircrafts are changing. Now, how do you visualize this changing behavior of the scan? Use the same static network previously and add a time component. So you have few snapshots of static network. So this is one snapshot for first 5 minutes. Then you have another snapshot of the strategy for 5 to 10 minutes. Then you have 10 to 15 minutes. Now you see the important aircrafts, like the size and the color of the nodes are changing. I deliberately kept the relative position of each of the targets same across these snapshots. So it's easier to control. It's easy. It reduces your cognitive load. You can directly compare figure 1, 2, and 3 and know, okay, aircraft F was most important on the first 5 minutes, but by the 5 and 10, it was reduced. If you go back to the radar, you see aircraft F was almost leaving the airspace of the controller. So now you can verify, yes, we can utilize. And you see the transition structure is also changing as we move with time. However, one may ask, okay, if we just show, but if the number of aircraft becomes too huge, even this dynamic networks gets complex. As you see, from 10 to 15 minutes, it's very difficult to see what was the actual transition between which aircraft, because it's too messy around there. So now the next stage comes, how we can visualize this knowledge or enhance the evolution further. Before going that, another utility of the network is you can use some mathematics from graph theory, which is called closeness measure, centrality measures. There are 3 major, I'm not going into details, but you can use these measures to find out different kind of importance of each node. The node translates to aircraft in our case. You find out how many times you visited, how close it was there with respect to the mental map of the air traffic controller. And betweenness refers to as how crucial it was in terms of the flow of the whole eye tracking strategy. Now you see how a graph theory measures can be translated to eye tracking and understand the decision making, or the strategy, visual scanning strategy happening. So this where analytics comes into help, and you can do all sorts of advanced statistical machine learning by building upon these measures. There are other measures I'm not going to. So the next question comes is, how do you visualize this evolution of scanning strategies? So I adapted few existing plots and developed one plot. The first plot is a dot plot and a bar plot, which is very intuitive to understand. The dot plot is you just show for one participant how the importance of particular target is changing over time. On the y-axis or the vertical axis, you have the time, and on the horizontal axis, you have the targets. You see the size of the dots are changing. That means their importance is reducing over time. For example, A, it was large in size A, and then it slowly reduces as we move. I can see somebody raise their hands, but I will address all the questions at the end of the presentation. That will be much easier. So hold your questions for now. So now, however, this has one limitation. You cannot compare across participants. You can compare across time intervals, but you can only show for one participant. If you can include, but it becomes too messy. So, however, to address this challenge, you go to a bar plot where you normalize the measures across participants and you compare. So this is showing for 3 subjects or 3 participants how the importance of different aircrafts was across different visual scanning types. So for A, it was the relatively most important for all the 3 participants. However, if you move to control aircraft B, controller the participant 2 laid most interest on that. However, for participant 3, it is not at all important. So you see the difference in the scanning strategies for the same aircraft. And you can build upon other plots. You can ask, what if the number of aircraft increases? How we can utilize this? So there it comes. We can use other characteristics of visualization like shape and color to indicate target importance. And another interesting challenge is the overlapping. you cannot, it's not very intuitive to show the bar plot with overlapping. It's a text. So how we can enhance those aspects? So what you use is you use different shapes and color. So if you're using alpha like English characters to represent targets, you can use a combination of shapes and color to identify across different or a number of aircraft. Now, how this helps is, now you see such a plot. You have different participant number, and you have the relative importance of various aircraft. So using shape and color, you can show a large number of participant data or subject data in a one snapshot. So how it is useful is, you see these small objects tied together, it is useful to show overlapping targets. So this is a nice visualization that I came up with. Then you have, and since this is a relative order, so if the symbols are on the left side, that means they are the most important for that subject. Now you can use the size as you move along the y-axis, the size also reduces to show that the relative importance of it. So why this is useful, you can directly visually explore and see there is similarity in the scanning strategy in terms of importance that they give to their targets. You see the inverted triangle with yellow color, first and second position for all the 5 participants. So there is, even though they are employing different scanning strategy, they are putting similar importance to the targets. So this is another way to say is there are numerous paths to the same destination. It is similar to what Ramakrishna Paramahansa said, Jatoma Tatopad, although this is a different context. But the thing is, you can employ different scanning strategies to give similar importance to the same aircraft. So this comes from the concept, the thing that there are heterogeneous ways of doing things, and there are multiple ways of doing how experts do. Moving ahead, the last plot that I will do, since we developed 3 important measures of target, all these measures were corresponding to one measurement criteria. Now, if you have to combine and understand overall, if we have to combine all these different important measures, which aircraft was the most important? Now, what I named this as a noncube plot, it is in reality is a normalized cube plot. Normalized because the important measures or the target measures were normalized between 0 to 1 because they have different range. So to bring it on the same plot, you have to normalize, and it's a cubic plot because it's cube. You have 3 axes. So you have closeness, in degree, and normalized, which we discussed. Now, how to interpret this plot is, farther away from the origin, the more overall importance, because the distance is from the origin, and higher the number of the importance measure, more important the target is. So if you're from the origin farther away, more important. And the color I have used to include the duration concept, because you might be important in terms of how many times you visited in terms of flow, but some aircraft, suppose they are in a conflict path to other aircraft, they might be spending very less time on the screen, but it becomes very important in terms of the whole traffic management. So you spend a lot of time on that for a very short span duration. Like the aircraft comes and oozes out of the sector, you just spend a lot of time seeing whether they are on a conflict path with other. And once they leave, it is no longer important. So this is very typical to dynamic scenarios. So what happens with static cases, if you spend a lot of time, or if you visit that target more number of times, we think that it is the most important. It is for static cases, you can translate, but for dynamic cases, you have to take into account duration and other aspects where you have flow of thing involved. So the last thing is, I'll not go much detail because I'm running out of time. So how do we simplify the scan path representation? Here I developed a quantitative framework using this spatio-temporal clustering. So this is with respect to the control tower, which we have seen previously. I did an experiment with the FA. So now you see the simulated in high fidelity environment. You have a out of tower view, which consists of the runway, the taxiway and all, and you have inside tower view, which have the computers and all. So these are the two visual. So aircraft enters on the left side on the runway, leaves from the right side, and was the environment I was working on. Now, what we did was, you see, this is a very 30-second scan path. On the top, there are two different examples of the raw scan path. To infer any meaningful, now this is just for 30 seconds. Now imagine for 1 minute or 2 minutes of scan path, you really lose a meaning, even though this is far more structured because the aircraft is coming from one side, it is leaving from another. You still have difficulty finding out anything meaningful if you have to just show this scan path and ask the controller or teach them what's the inherent pattern. So one aspect is, can we simplify this using some quantitative way, and can we then use it? So with that objective, what we did was, we have to, since we cannot use the raw, what we need to simplify it. Two criteria we have to retain is, the geometric shape of the scan path is important because the shape has some meaning. If you are moving in some fashion, that means those areas are important. If you're spending some time on some particular target, that means that target is important. So you have to take into account these things. So simplify while retaining the shape as much as you can. So because there is some semantic meaning of every part of that screen. How do we do that? There's a three-step framework that I developed. First is, you implement a clustering algorithm to simplify the shape. Here I used spatiotemporal DB scan. It's a density-based clustering. We'll go into detail. The second process is, there are a few parameters involved in these scanning. So how to include the context knowledge into finding the best simplification. So this framework actually helps in that. It gives a quantitative way to first define how much simplification is useful, and then choose the best optimal parameter given the context you are working. So with a different context, you cannot have the same optimal value if you move to a different context altogether. And the third step is how we can use further visual attributes like color, shape to further enhance it. So I'm not going into details, just giving a brief overview. This is a density-based clustering. If objects or targets are placed, data points are close here, you can use Euclidean distance or other distance measure. You identify them into a single cluster depending on how big is your space threshold or the distance threshold. You can also identify noise. Noise here means outliers. So this is one Wikipedia, I got it from the KDD. So here is all these, you see a red cluster. These objects are closely packed. Then you have a blue cluster, you have a green, and you have a yellow cluster. And some other points which do not belong to any of these clusters, they are considered outlier. So you have a continuous stream of closely packed. So all these red regions, one point is close, another point is, it's a chain of closely packed regions. So that's one beauty of this. This has been borrowed from the computer science domain because they use it in database analysis also. Then we used an extension of this DB scan called ST, which is spatiotemporal, because this allows you to define distance or proximity in terms of space and time, because these are relevant for eye tracking. You have a pixel location and the duration. However, one thing is, so the challenge here is you cannot directly use the raw. However, if you keep on abstracting, the raw is highly complex. You cannot directly use it. However, if you do a lot of abstraction or simplification, it will be very less complex. However, it will not be useful for training. So you have to find a middle ground, which is somewhat complex. It is still manageable and useful for training. So how do you find this trade-off? That's what this framework helps you to do. First is you implement the algorithm and find the best parameter value, which reduces the complexity. Now you have to define what complexity is in terms of this, and while retaining the scan path shape meaningful. So how do you first define them? So you can define complexity by using how the geometric shape of the scan path and the content of the scan path. Content here I defined using the number of eye fixation in the scan path. And geometric shape is obviously the shape. So how do we measure it? The change in complexities, number of fixation, content, which is directly related to the cognitive load. You have to you have to spend cognitive resource to actually understand the pattern, and it is directly, if you have more number of eye fixation, you have to spend more cognitive resources. And the last is you can use dynamic time warping, which is a concept to measure distance between time series data. You can represent the scan path as a time sequence. The scan path sequence is actually a time series of characters. So now you can use this concept of some time series to measure difference in how, once you have done the simplification, how different it is from the raw one. Using these concepts, I played with various parameters, and on the y-axis, you have the average number of eye fixation, which is proportional to the cognitive load, and you have different space and time thresholds. Now you see, as you increase the threshold values, the complexity reduces rapidly. But after a certain time, the rate of decrease is flattened out. So now you have to use this information to see which parameter combination gives you. So for this particular case, I found out that 200 pixel and 1500 millisecond threshold were the best for our case, because it almost gives 50% reduction of cognitive load. But this is not all, because you can say if you further increase the time, we can reduce much more reduction. You have to take the another aspect, which is the shape of the. So here I plotted on the y-axis, which is called average normalized DTW distance. So basically, in simple words, it measures, you are given a raw scan path, raw data, you simplify it, how different they are in terms of their shape. And you do it multiple times and normalize it. Normalize it, that's why it's normalized distance, because across participants, you will have different lengths of the scan path. And average, because you are combining different subjects, different trials. So average, normalized distance. So here you see the maximum differences. If you keep on increasing the threshold, you will have such abstract or simplified scan path, which will be 700 units from their raw counterpart. So in the middle, you find a 300 around. So that's where 15 and 200 comes from. So that's why I use such a threshold. Now, the last step is, once you have simplified, find out the optimal, how can we visualize it, enhance the visualization further. So on the left, you have the raw scan path. The red circles is when you use those thresholds, implement the clustering. The clustering happens on those red regions. On the right, you see how you can further enhance this simplified using color. So you can use yellow to red transition. Yellow means older fixation. Red means recent. Why it is useful? Because if you are plotting scan path for a longer duration, you will again have the problem. If you use the numbers just to define, you will have multiple numbers and they will overlap, as you will see in the example. Then you don't know which happened at what time, because you cannot read because of that superimposition. So you can use the color to give some visual cue. Okay, this is how it flows, because the flow is also important, not just the shape. And the black border around those circles shows that yes, clustering happened. So you have to take that scan path with a pinch of salt, that there are numerous other fixation happen in that region. So I might spend more time in those regions where the clustering is happening. How that translates into two commands that I played, I'm showing here. It's clear to land. It's like giving an instruction to an aircraft that you are okay to land on the airport. So you see, it's a 30-second scan path data. You see, there are many numerous fixation, but you know where to start, where to end, because you can't see 1, 2, 3. Just as I mentioned, if you are representing with the number, they overlap, you lose. If you simplify that, now you can use the color, even though 1 is not visible, but you can see there is a yellow thing. Then you have slowly 3, 4. So you have reduced the number almost by 1/3, and you can use the color. You see there is a triangular shape happening, and it starts from the runway region. Then it comes back to the representation on the computer screen. It goes back like this. So this is one example. There is another example of clear to land. It reduces the cognitive effort, but we need studies to prove that. But just from visual exploration, you can see you have to process less information, and you can still preserve the overall shape. Another example with clear to take off. You're giving an instruction for the aircraft to take off. This is a little simpler, but here it is getting complex because of the numbers. You simplify it with the same threshold, and you see you can preserve the pattern and it's just few fixation. So you started at the screen because the yellow showing that, you move to the left side of the runway, then to the right. So it's much easier to teach to somebody. A similar example. Now concluding my talk, the first one, we talk about how to effectively visualize the scanning strategies. The first component was adapting a dynamic network-based approach to map eye tracking data, show it over time in terms of network, use their importance measures from graph theory, and use those metrics to quantify the scanning strategy. Then use those, you can visualize those measures using another visualization, dot plot, bar plot, cube plot, order plot, which gives a further crisp view of what happened in that complex. And the second was a simplification of the representation of this complex scan path. So you can use a clustering quantitative method. You can tweak the parameters. Now you have a framework which helps you to take context knowledge and find your best optimal, because it is very difficult as you change the context. You can use, after simplification with that added color and shape thing, to show a much clearer view to the novice controller for that training. That's all from my side. Thank you. Now questions, if any.
Thank you, Saptasida. It was a very informative and very interesting talk. And Saptasida, we have received several questions in the chat box. So I will take one by one. The first question is, how do you filter out noises from eye tracking movement data, like random eye movements, involuntary eye movement, etc.?
So there are few algorithms which is now already implemented in the commercial eye trackers. You have distance-based IVT, IDT. It's basically you use a velocity threshold. Those if the person asking, they must look up these algorithms. These are well established. IDT and IVT. Many other algorithms are coming. It's like you take the speed of the eye movement, because there are some values that you obtain from psychology basic research, like how do you define a fixation? It's like, depending on the context, that fixation definition start from, if a person is locating within this particular region and the duration exceeds from 60 millisecond to 100 millisecond, you define it as a fixation. So it is not a hard and fast threshold that this is noise and this is some, but you have to incorporate these contextual knowledge. So that's how you can identify noise. Another in terms is, if I'm not sure the person is asking about blinks or saccades, or it is just eye fixation noise in general, like fixation noise or noise in terms of other things. So I'm guessing it's terms of fixation. So yeah, these, and there are few recent algorithms that I have seen from MIT is like, they use also a clustering technique where they use, I think similar to distance-based thresholding, like you pose a distance-based, like distance threshold and define the cluster. So it doesn't require those millisecond taking 60 millisecond, I will choose that as a threshold and then, but it's the unsupervised way of defining fixations and all. That's how you can do it. And that's the best, to my knowledge, that I can say.
Thank you, Saptasida. Now the another question is, given that there are numerous scan paths that expert use, how we can develop an expert model to show it to the novice? Yes.
Yeah, NASA tried that, automating these processes in an airport, not even en route. They failed miserably because of the dynamic aspect. So the objective is fine. Even my objective, and like many people working in this domain, their objective is also going towards developing an expert. One starting point is to first make an exhaustive list of how experts do it, because we don't have a standard way defined that this is the best way given this scenario, because this scenario is not even defined. It is changing because of the weather and other aspects that I said. Weather is a big thing. And as a result, you don't have first a list of the best. You don't have an exhaustive list. So you cannot build the next stage, which is the expert system. So first, this You have to see how experts do it, treat it as a gold standard, then use that as an input to the expert system. So we are still at stage 1. What the audience person is asking is, how do we develop the stage 2? Once we are able to sufficiently understand stage 1, then we can formalize these knowledge of experts. But in reality, when I have talked with numerous expert aircraft while doing this research, even they find it difficult to verbalize, because all these knowledges are tacit in nature. Tacit, in simple words, is you gain this knowledge by doing it. You don't have a formal way. Okay, step 1, scan here. Step 2, you develop it while doing it, and it's you can say unconsciously you have that with experience. And it's if you ask them how do you do it, they can give a very brief overview on a very top level. They can't pinpoint why they were doing it. So when I showed them the recording, they were also thinking, why did I? Okay, this might be the reason. That's why I looked here and then I switched there. Then they are able to verbalize some of their strategies. So many of my research, along with other colleagues, we wanted to formalize this tacit knowledge into concrete like strategies, like how many times, what is the overall geometric shape of the scan. And once we have this list, which is not obviously exhaustive, but it changes with airspace, with other aspect, traffic flow, we'll have, once this list is, we'll have some pattern extracted from that. Data analytics will help in that. Use that to build a preliminary expert system. So that's the way I think. That's a one way to do it.
Thank you, Satyajit. Another question is, in the scan path analysis, if the two operators have similar scan path, but their duration varies significantly, so does this signify differences in their cognitive ability? Yes.
Is it only with respect to experts or in general? So if it is for experts, in general, obviously the duration has difference because the shape and duration both make the scan path strategy. Goldberg, I think, did some research, early research in 90s in analyzing user interfaces with using eye tracking, and he find duration as duration has high correlation in how easy is it for the user to understand what is given on the interface. Suppose there can be two ways. If you are looking at an object for a very long time, either the object is very crucial for you for the job, that's why you are spending on time, or you might be having too much difficulty in understanding what is object doing there. So there can be both ways. So for experts, if they are spending, so what I observe, especially in this air traffic control, is counterintuitive to experts do have very less duration and they do numerous transitions. So they keep on looking continuously. Whereas novices, they spend much more time on some aircraft, then move to. So they, even though the shape might be same, but their duration is much longer. So since we already defined somebody as experts, we have to take into account this. If you change the context, it's like some contexts have safety critical aspects. It's like in a time bound, you have to finish this objective. That's why they have to continuously scan. So there is a context involved in that. So it's not necessary that if you're spending longer duration, they have a high or low cognitive. It depends on the scenario you are working. For air traffic, higher duration is mostly observed in novices, whereas experts have more fixation continuously with less amount of duration, because they know once they have developed the map of the mental map of the traffic flow, they don't spend much time on reading each aircraft. They continuously scan and continuously update their mental map. And if they have to resolve a conflict, then they go into those altitudes and read their speed and in that order, and then destination, and then they define. So it is not a one answer for all contexts. Higher cognitive duration means higher cognitive. No.
Yes. Thank you, Saptasida. With your permission, I am taking the last question. Apart from DB scan, what kind of clustering technique can be used
for this simplification?
Yes.
So this simplification, there is another technique already people have done, but you have to so the objective is there has to be something which is doing with space and time. So there is one paper from Dewhurst. I think it came around 2019. they also did a similar scan path simplification, but they took a threshold of 10 pixel width or 10% of the display width as a threshold to do the spatial thresholding, which I didn't. I took a unsupervised thing. I played with numerous things and didn't stuck on 10% of the display size. I found out if we play or change this parameter with how can we take into account the context knowledge. They also did a similar simplification in a different approach, but they didn't provided a way to take into account this context specific information into that simplification. This framework takes into that. So there can be multiple ways, but ultimately a simplification of a pattern means you simplify their shape, you aggregate close by fixation into one. So I think I'm not sure about exact technique names, but any technique that satisfies these two criteria can be used. So TV scan was giving me a density based. So that's why I used that. So density here is spatial density and temporal density.
Thank you, Saptarshita, for your explanation. Now I would like to invite Professor Krishna to formally provide vote of thanks to our expert speaker. Over to you, sir.
Before I get into this, I want to ask any participants want to ask any question to Dr. Saptarshi? Unmute to all the participants.
Yes, sir. Participants can unmute themselves.
Good evening, sir.
Good evening,
sir. Muralidhar here from Bangalore. Thank you for your good presentation. I have one query, sir. What is the percentage of human error allowed in ATC?
Controversial question. You shouldn't be asking in a public domain. I have to refer to a expert document. I can just give a number and be in trouble because I am. So,
thank you.
In reality, I can give you statistics not with air traffic controller but with pilots. It's the major human error is the major reason for pilot errors, and because I was working with one of my colleague in that human error aspect and how fatigue impacts human error. Most of the airline crash or mishaps that happened due to, and the major reason was pilot error, and it was due to fatigue was one of the primary concerns. So ultimately it's always human error, whether it happened due to environmental reason or standard procedures or other aspects. But the final stage of when the mishap happens is always the human because they are providing the input. So
yes, as a safety professional, we address it as unsafe act.
Yes, but it's easier to always blame the operator or the pilot. But it's like if you are going into a blame game, it's always easier to blame the final person. But we never. It's in the long run. It's always we should take into account the environmental aspect or what are the reasons that led to that failure. Is it just because of carelessness or other aspects that they had no clue what to do at that scenario?
Yes, sir. Thank you for your response.
Actually, colloquially, the pushing of the blame, one in the fire incident on short circuit, people push it if they don't anything. In the human, they put it unsafe act. Very colloquially, people keep on putting. But we know from DuPont and other places, there are a lot of differences in this. Any more want to ask? Anybody want to ask any more question to Dr. Saptarshi Das? Yeah, okay. See, let me tell you, Dr. Saptarshi Das, your talk is...
Oh, I am changing my surname.
Huh?
Dr.
Yeah.
Saptarshi Mandal.
Saptarshi Mandal, not Dasi.
Saptarshi Mandal, sorry. Saptarshi Mandal, sorry. I'm extremely sorry. You see, then there should be eye tracking to me also. When we hear to such serious talk, so it will be difficult for the participants. All that's what we are facing in the online teaching nowadays. The students are facing a lot of problems. The faculty is facing a lot of problems. our mind becomes dull many times. Saptarshi, good. You made such a serious talk into two parts, as I have seen. A generic information to all the people so that everybody can appreciate the whole system of these aeroplanes, ATC, the controller's job, and all these things. I learned many things. I sat many times by the nearer to the pilot, by the side of the pilot in our Tata Steel captive pilots. I used to hear from them, but I never heard so detailed about the ATC what you have mentioned. And you've also dealt for those who are really working in this field, a detailed, in-depth knowledge also you're shown. Very excellently articulated the whole talk. Thank you very much. And I never thought the ATC controller job is so difficult. I never visualized that the ATC controller job is. And the second thing you mentioned about the atmosphere, see the environment, the prediction is so accurate nowadays in the land. When it goes to the top, when you say that it is very unpredictable because we don't have such models. What we see in the our people predict very clearly nowadays, and evacuation, all those things are done so accurately. Is it not possible? Why it is not possible in the say high altitudes?
Implications are different actually. Suppose a land weather forecast says at 10 o'clock it will be heavy rain. So I have to carry an umbrella or I have to sit inside. That's it. But for a pilot who is outside, you have to actually guide them what to do, how far away I should be from the thunderstorm. And all those implications come with that prediction. And as you move up on the stratosphere, the change is much more dynamic. So that's a basic difference that comes in. As you come down, the change happens much more it takes much more time to do such rapid changes. So that's one reason. Because mostly another is if you're flying high, you are much nearer to the thunderstorm. Whereas on the land, you just watch it from a distance. Unless it's falling on you, you watch it from a distance. So those implications are completely on a different magnitude, and the pace is different. So
nice. It's a very good explanation. Very good. Thank you very much. Thank you very much for your answering the questions and taking so much of time for explaining the concept to the participants. Professor Maiti, you want to say anything?
No?
I want to thank all the participants because it's Friday evening there. Lecture, I'm surprised. They must be very dedicated. All thanks to them.
Yeah. Actually, I want to thank Dr. Mondal. Really, you made that evening very useful, and some of my scholars will be heavily benefited, and I hope that they will use your models also. Thank you so much.
Okay, thank you. And I need not separately tell the participants, you have actively participated, you have heard. For such a serious talk, you were all there throughout right from the beginning to the end. Thank you very much. And my moderators, Sween, Ashish, Savik, thank you very much for your very well coordinating the whole such technical event. Thank you all. Next week again on Friday we'll have industry speaker this time. You will not have such a very deep academic subject. It will be very industry speakers talk very light subjects. Thank you very much.
Not allowed to talk about Microsoft subjects due to NDA. That's why I chose the PhD.
And I should tell people when Saptarshi Mandal says after some time I'll come back to India and do work here. It gives me a lot of motivation to see people like you that you want to come back and do something in India. All the best, Dr. Saptarshi Mandal, to your thinking and to your efforts. Thank you, and we close the session in this place. Thank you all again.
Thank you,
Thank
sir.
you, everyone.
Thank you, Saptarshi.